So this is a basic layout of the air data reference unit. You can see by the word, the air data reference unit is, there are two on board, but it's two halves. There is an inertial reference part and an air data reference part. And the whole unit is called an ADIRS, okay, because it's a combination of air data and inertial reference. And we said the air data creates airspeed and altitude, and the inertial reference creates all the other stuff. We have all the pure analog signals, pitot pressure, static pressures, total air temperatures, angle of attack information, so angular displacement of the aircraft, so to speak, going into these air data, into these ADIRS, and coming out of the ADIRS are the ADR data, and the IR data will then go to the do everything boxes and then be displayed onto the different displays that require it. In order to start it all up, I have to actually switch these on. So for ground operations, they're usually not on because if for any reason, I don't know if you ever worked or saw a gyroscope or even an ADIRS nowadays come in a box. It usually has this thing says handle like eggs, even today. All right, even a laser gyro that has no moving parts, yeah, per se, still is treated as a very delicate object, a very delicate box. They're very expensive, okay, and you're not supposed to move them inadvertently while switched on, while they're thinking of their current position. You're right? Because if you do that, they will go out of sync, they will stop aligning, and the alignment process will have to start again. And you'll see that the alignment process is a bit laborious. So if you're rushing to go and you do anything out of sync, then the alignment process stops and you've got to start again. And then where you think you're cutting corners and saving time, you're going to end up with more delays and end up with an aircraft delay or on pushback. All right, so we have to, the MSU is to switch them on and off, and for fault indications, as you can see, it's just full of lights and just two knobs here, control knobs to switch them on and off. And the ISDU is here to provide information, additional information to the ADIRS that we can manually input. For example, present position, we can manually put it on this keypad, press it in, yeah, input it. In the olden days, in some airports still have, when you get to the gate, there's a big post there when you see the guidance system to bring the aircraft in, where the pilot is just looking and it's like lights, 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 and stops, and the pilot knows when to put the brakes on. Or on that post above it, usually there is the present position. The present position, the GPS present position, in terms of latitude and longitude, like this display here. Okay, so if the pilot wants to manually put the present position in when they first get on the aircraft, they only have to look up and copy what is above that guidance system and put in the present position. There are other ways which we'll look at in a minute. In terms of the location of the components, mainly the displays is where all the navigation information is going to be displayed. Okay, and then the ISDU and the MSU up here on the P5. We have another IRS select switch here, but mainly everything is in close vicinity in the view of the captains, of the pilots, because they're looking at navigation and statuses, they're looking at scenarios, they're looking at how their aircraft is behaving relative to ground stations, relative to the altitude, and relative to the weather, so to speak. The two boxes, left and right ADIRS, are in E5. Okay, so this will be if you're looking forward. So this is the E&E bay, and you are looking at 3 o'clock position. The 3 o'clock position. So this here is E1. This is E1, and this is straight ahead. So this is the nose of the aircraft forward, and this one will be at 90 degrees, 3 o'clock position. And this is E5. That's where your ADIRS are. And just while we've got this picture up, the ADIRS are outboard of the flight management computers, which are also going to be used in talked about today because we're doing navigation and the flight management computers do the flight managing. Other than the pitot and the statics, we have the AOA sensor, angle of attack sensors, okay, and the TAT probe. The angle of attack sensors, as we said, give an angular displacement of the aircraft because they're set to move in the airflow, and as the aircraft moves, it changes its pitch. These sensors align themselves to the horizontal plane and complete or produce a displacement angle. And this displacement angle is equivalent to the angle of attack of the aircraft, which is taken then as pitch data. It's converted through an ADM to ones and zeros, and then it's displayed or sent to the ADIRU that can understand the pitch, the pitch of the aircraft, which is part of the attitude of the aircraft, which it produces, the picture of it. When we say attitude, it's not angry, happy, sad, sorry. It's the state of it. So it's and the attitude is usually pitch up, pitch down, okay? Nose up, nose down, or left wing up, left wing down. Oh, yeah. So these are the state of the aircraft as it is in abstract, in space, and everything in between. The actual boxes themselves, the ADIRS, the Air Data Inertial Reference Units. This is what they look like. There is no bite on this box. No, there is no built-in test equipment on this box. So this would be an indication that this box is actually, or the system is tested on a dedicated menu on the CDU. Okay, so that's how you can tell, guys. If there's no menu, if there's no byte facility on the box, which you'll see a lot of today because every box has we have to see how it tests. Anything that's got a byte on the box, tested on the box. Anything that doesn't have a byte on the box is tested on the CDU. So here is the SDU. It enables the pilots to view data and manually enter the present position. Okay, present position. If you selected here, the present position, it would accept you putting in the present position. And look, it's got all these. It's got north, south, east, west as well. It's got all the parameters that you can put in terms of the mode select unit, the MSU. We said we can switch them on and off. Okay, and we have a load of lights here to indicate the health of the health and mode of which the IRSs are in. Okay, now of course this is a new inbuilt box because the older aircraft, the classics and the Jurassics, didn't have inertial reference units, so there was none of this switchery here, none of these indications. Okay, and because there was none of this, we had to install another box. This is on P61, just behind the co-pilot in that little alcove. Okay, the IRS master caution unit, that makes all these cautions come up because, as I said, this is a supplementary modification. All this didn't exist in the old models. This is a typical angle of attack sensor. All right, the electrical connectors that take the information, the angular displacement. So in here you'll have a sort of a synchro mechanism where over 360 degrees you have a coil, a pickup coil, and another circular coil over 360 degrees. And wherever that coil, the pickup coil, is turned, okay, it will displace. It will make an angular displacement, which you then can electrically send to a ADM to convert it to then ones and zeros. The other ADMs that take pneumatics, the pitot and statics, they'll just go in through here. Pneumatic pressure or static pressure going in, and ones and zeros coming out, going to the ADIRS. TAT is not the outside temperature. OAT is the outside temperature. The total air temperature is used by the flight management computers to calculate how much N1 you need for the engines, how much thrust. So we're going to see later on, further down the line, that the FMC's sole purpose in life is to save fuel, to calculate the most economic route from takeoff to landing from A to B, okay, to save fuel. So in order to make it the most economic flight from takeoff to landing, we have to adjust the N1, so the thrust, so that we're not overspending fuel. Okay, we have to become as efficient as possible. Now, the temperature has to be known to the engines, to the ECUs, to the ECs, because it's integral to the calculation of how much fuel is required. I'll give you the example of you're taking off in London where the outside temperature is 4 degrees and the air is very, very heavy, and therefore you don't need as much chopping of the air, yeah, as you would need in Bahrain, where it's 42 degrees at lunchtime and at sea level, and you need to chop a lot of air to get the same amount of thrust. Okay, so TAT is a very, very important factor, very, very important parameter that the engines need for N1 calculations. Okay, the OAT, once we know the TAT, we can then calculate the OAT. And the TAT is, even if we lost this probe, okay, we know, I don't know if you remember from your physics from year 10 at school, that the temperature drops, and there is a graph with a known sort of temperature decrease per 1,000 feet, yeah, as we increase our altitude. So we know what the total air temperature is as our altitude increases, but we're just taking the information, the TAT, so that we can calculate the OAT as well. All right, and it's just a reaffirmation. Yeah, we can't just rely on any old data, because that formula that we've got to calculate the TAT as we increase it in altitude, it is used for a standard atmospheric day, okay, at 1013 millibars. And it's not a very common phenomenon, 1013 millibars. Okay, so the local atmospheric pressure is not always 1013 millibars or 79.92 inches of mercury. Okay, so therefore we need an indicator. We need one of these instruments to be able to tell us the TAT at all times. What we also need is to know how the IRs work in general. So they are 3 axis gyroscopes. So they calculate our position over 3 axes. All right, the X axis, which is for the pitch. Okay, the Y axis is for the roll, and the Z axis is the lateral for the yaw. Those are the 3 axes. So we have 3 laser gyros in 3 planes and 3 accelerometers.